In this video, we are going to talk about an example involving simple harmonic motion. A motion follows a sinusoidal or oscillatory type motion. So first thing I'm going to do here is I'm going to draw a picture of the motion, position versus time. And I'm going to use a cosine wave here to model that motion. And the given says that the peak to peak value, or the distance from the peak to a trough, peak to peak here, is 36 centimeters. So 36 centimeters is this distance, centimeters is this distance from top to bottom. Okay, and the other thing that we're given is that the time from one point of zero velocity to another point of zero velocity is 0.25 seconds, a quarter of a second. So this time is the time from one point of zero velocity to another. So we need to take a look at that in a little more detail to see what that actually means. So in this problem, we're going to find a couple different things. We want to find A, the amplitude of the motion, B, the period of the motion, C, the frequency of the motion, and D, what the maximum velocity of this object is. So we follow the three-step process here: list equation, list variables, and solve. So for the equations, we're going to list these equations here. We're going to list the position versus time, which is the x max, or amplitude, times cosine omega t plus phi. And then if we take a derivative, then we're going to get minus x max omega sine omega t plus phi. And finally, the acceleration versus time, which is the second derivative of position with respect to time, is x max omega squared cosine omega t plus phi. And then a couple other equations is period equals 1 over the frequency, and also that the angular frequency is equal to 2 pi f. Alright, so and there's a couple other equations that relate to the frequency and the periods to the spring constant for mass on a spring and length of a pendulum and so forth, but I'm going to stick with these right now unless we have a specific type problem with those. So what do I have here is I have x max, I have omega, I have t, frequency. Those are my unknowns. And so we're going to solve here, or go through what we don't know before we solve. So let's see, x max I do not know, not given. Omega I don't know. Period, I'm given a time, but I got to make sure that's the right time for a period. So before I fill that in, I'm going to list that as an unknown, and frequency here. So let's go ahead and solve this. So part A, the amplitude. The amplitude, as we know, is the distance from the center line to the max point. So if 36 is the total, then x max by inspection is half of that, or 18 centimeters. So by inspection, we can just read off the picture there. That's why this picture is very important, so we can draw things on here so we can make sure we know exactly what we're talking about in terms of amplitudes and frequencies and so forth. Part B, let's find the period. So this is the interesting part. So we're given this time that says the time from one point of zero velocity to another. So this is displacement versus time. So let's draw a little graph over here on the side as a side dish and take a look at the velocity versus time graph, because that'll give us some insight as to what this time actually means. So I'm going to replicate the position versus time graph here, which looks something like this. And then right below it, I'm going to draw the velocity versus time graph. so I can see exactly where these zero velocities are. So if let's see, I'm going to match up some lines here. That goes down there, that goes down there, and here, and there. So if I take a look at the velocity versus time graph, it looks something like this. Let's see, the slope here is 0, slope here is 0, slope here is 0. Here I have a negative value, and here I have a positive value. So this graph can look something like this. That's my velocity versus time graph. So let's see what this 0.25 seconds means. The time between one point of zero velocity here and another point here is 0.25 seconds. Which is not a complete wave. A complete wave would be all the way over here. So if I have another 0.25 seconds here, then the period or time for one complete wave, as you can see here, the period is actually 0.5 seconds. But that's the time for one complete wave. The frequency therefore is, part C, is we can use this relationship here, 1 over t, or 1 over 0.5, which is 2 hertz, 2 cycles per second, 2 waves per second. D, the maximum velocity. So how are we going to find maximum velocity? Well, as we can see here, this object reaches a maximum velocity right there and a maximum velocity right there, and will continue to do so. So what is this value right there? Well, if you take a look at the equation for the velocity versus time graph, it's basically the coefficient of the sine function, which is this guy right here. And xm, or amplitude, times omega will give you the magnitude of that amplitude. The minus sign, as you can see, just merely flips around the sine graph. The value on the upside or the downside is omega m, xm omega, or if we're talking maximum acceleration, it's this coefficient. So just think coefficient of the function there. So Vmax is the amplitude of that function, which is, and I'm going to talk about the magnitude of it, is basically xm, which we already know, times omega. And omega is really 2 pi f. 2 pi f, and how do we know that? It's right here, which goes to the explanation of how this relates to the angular frequency of an object that undergoes motion in a circle, which we talked about in class. So if I go here, I've got 18, this is in centimeters now, times 2 times pi times another 2 for the frequency. And when you do all that, you get a value of 2.26, or excuse me, 226 centimeters per second, which would be 2.26 meters per second. 226 centimeters per second. So this value literally is, on the negative side, negative 226 centimeters per second. On the top side, plus 226 centimeters per second, since that's the unit I was given. So in solving this simple harmonic motion problem, strategy is to draw a picture of a wave, and the picture again can help you describe what quantities are where. We're given the time from one point of zero velocity to another. We have our find here. The equations are your x as a function of time, position as a function of time, and you can take two derivatives to get the velocity and acceleration. And then we have a relationship between period and frequency and our angular frequency. We listed our variables. And again, as you saw here, the most important thing is to really look at these diagrams. These diagrams tell you a lot about the motion, especially about this number here, how it's could easily be mistaken for the period, which it's not. It's half the period, and so forth. So these are the steps you would follow to solve a simple harmonic motion type problem.